Okay, so moving on, something you want to know about in the lab is how on earth do you find the electric field at some point when you don't know the direction of it even. So I've sort of sketched out the problem here. Here's one point where you're supposed to find the electric field, and here is a grid of points around here. We're going to assume we know the voltage at all those points because that's the problem you face in the lab, right? You took a bunch of voltages, a bunch of electric potentials, and you figured out, well, you took them all. Now you've got to figure out the electric field everywhere. So here is what I'm going to start with. I'm going to define this here as our delta R vector, which means I'm going to need this voltage here. I'm going to call that VL, and this voltage here, which I'm going to call VR. Okay, so this here is our delta R vector, goes from left to right, and I'm going to say delta R then. So I'm going to, use the equation relating the electric field to the change in voltage. Okay, so delta R here is going to be, now I've said these guys were separated by a distance of d, right? Each adjacent pair of points. I think that was 2 centimeters in the lab. I'm going to, so I'm going to use that as my dimension here, my measuring stick, so to speak. Delta R is 2d long, so it goes in the x direction. So the delta R is 2d I hat, and then your VR minus VL is your change in voltage. Okay, that's the delta V you need to use. So now plugging this in, I'm going to go delta V equals E dot delta R, right? Now we don't know what the electric field is. So I'm going to have to represent the electric field in sort of a general form and say the electric field, and I'm going to go with blue here so my colors can work out neatly. So I'm going to say the electric field has an X component and a Y component, right? That's generally what we assume. We're not going to worry about a Z component here. We're not going to be able to find it anyway, and you'll see why. So, but there we just sort of assume there's no Z component or it's negligible. So here we can then plug in here, and we can go VR minus VL. Okay, that's our delta V here, right? Then our electric field is EX times I hat plus EY times J hat. And then we're going to dot that with our 2D in the I hat direction. Okay? And so, what happens here is when we do the dot product, you'll notice this term here, the EY times J hat term, that's going to go away because we're dotting it with a vector that only has an I hat component. So what you're going to get is VR minus VL equals, oops, I forgot the negative sign, negative. That's kind of important. Sorry about that. Okay, negative EX times 2D. And what you'll get there, then, when you rearrange it, is that the X component of the electric field is equal to the change in voltage as you go from the left one to the right one, divided by the distance from the left one to the right one, which is 2D. So what this does is this gets you an approximation of, I suppose it might be more appropriate to do an approximate equal sign, but this gets you an approximation for the X component of the electric field at this central point. So remember, I said this only works as an approximation if the field isn't uniform, and the field is not uniform. It's changing, but it works pretty well as an approximation, and it works best halfway between, which is exactly this point where we were supposed to find the electric field. Okay? Now, the next thing you need to do is, you say, well, that's great. We've got one component of the electric field. Where do we get the other one from? So let me take this disgusting-looking pastel green color and say, okay, now we've got to do this again, and we've got to take a vertical hop like this. So we know the voltage, which I'm going to call, I'm going to call this VB. It's the voltage at the point below, or the point at the bottom. And this is going to be VT for the voltage at the top of the little square, okay? And so now, when we're doing this in green, I'm going to do this, completely differently. Well, it's the same thing, but I'm going to reuse terms that I used in red, so don't confuse the green and the red. So now delta R is 2D, you're going a distance of 2D, and you're going up, so we're going J hat, and delta V is going to be V top, where you finish, minus V bottom. And what that'll get you is that the electric field, the y component of the electric field, is going to be Vt, oh my gosh, negative sign, I forgot the negative sign. Okay, so it's going to be approximately negative Vt minus Vb over 2d. Okay, so there you go. And in red, oh my gosh, well, hope you didn't finish, hope you didn't turn off the WebAssign or turn off the video before now, because you're going to miss this. Very important. Okay, so then this lets you solve, using these 4 voltages all around, it lets you solve for the x and y component of the electric field at this central point. That's what you need. If you're wondering, that works great. How do we do it if we're, oh crap, I don't want to be there. How do you do it if the point you're looking for the electric field at is on the edge of your rectangle of data? And the answer is you can't do it. So don't. Anyway, hopefully that helps a bit, and good luck.